Okay, so last class we already started discussing clustering, and generally speaking, we said there are three approaches. Okay, the k-means, and we have already discussed k-mean. So what today we will discuss is about the hierarchical clustering trees. Okay, and the third one is density based. And all this under unsupervised learning. Okay, so the target value or the target classification, we don't know. Okay, so that's the general idea. And then let's move to, so we already know k-means. And so what today we will discuss is about clustering. Okay, so over here, so the clustering, what we are going to discuss is called hierarchical clustering. Okay, and this is also prototype based. So for the clustering, how it's going to work is we are going to plot some diagrams. We call it dendrograms. So the dendrogram is kind of like a visualization of a binary hierarchical clustering. Okay, then that can help us to interpretation of the result. And if you recall previously, the decision tree, we also borrowed the idea like using visualization, okay, to help with the learning. So here we use another kind of plotting, we call it dendrogram. Okay, so we will see. And because of, like for k-means, so we need to, up front, we need to specify the number of clusters that you want it to try, is it? But with this hierarchical clustering, there is no need for the number of clusters beforehand. Okay, so that's a major difference. Okay, and for hierarchical clustering, there are two approaches under it. One is called agglomerative clustering, and the other is divisive clustering. Okay, so for divisive clustering, then it start with one cluster. So all samples going to be included in that single cluster. Then we iteratively split the cluster, the bigger cluster, into smaller cluster. Okay. I said until each cluster only contains one sample. So that's divisive. And on the opposite side of the divisive is agglomerative. So agglomerative is start with each sample as an individual cluster. Then we do the merge. Okay, we merge the closest pair of cluster until only one cluster remains. But you may say, okay, only one cluster, how are we going? So we will see, we will have some cutoff values, okay, so that we can identify the number of clusters. So that's general idea. And regarding the agglomerative hierarchical clustering, so agglomerative, it's start with one sample as one cluster. Okay, so that's agglomerative clustering. Okay, one sample, and then you merge clusters until you only have one cluster. So that's how agglomerative work. So then it's, here it involves the merge, is it? So what kind of matrix that we use for merge, is it? And how are we going to merge? So there are different matrix, and the different approaches. And the two standard, one is called single linkage. The other is called complete linkage. Okay, and there are some other we will see. So let's see the example to better understand single linkage and complete linkage. And here, because we are going to do the merge. So merge, then it needs to be based on some metrics. Is it based on some metric? So here we use what? Cluster distance as our metrics to measure, okay, to measure. So regarding single linkage, so over here, we can see is that so we have, because initially is that you have each sample is a cluster, then you kind of merge. So just assuming right now you have merged and you have your samples classified. So this is one cluster as red color. This is a yellow color cluster, and here we have the blue color cluster. Is it? Then we try to merge two clusters. So we try to merge two clusters. So we are going to use some measure distance. And for single linkage, the points how we pick is we pick two closest elements in the cluster. So two closest, so you're going to measure like, so suppose for this point, is it you're going to measure its distance with all of the other points from other clusters, is it? And then we are also going to kind of then measure other points with all of the points, is it? Then among all of the distance, the pair of distance, so we pick the minimum one. So we can clearly see in this diagram, the distance between these two is the minimum one, but it's from two different clusters. That you pick the distance, that's the minimum one. Okay, so between the closest element. Okay, and then you say, okay, I'm going to merge these two clusters together. Okay, so that's how this is going to work. You find the closest element and then you merge. So this is one approach. And the second approach is called the complete linkage. So complete linkage, the distance is the distance between furthest element in clusters. You don't measure distance within cluster, only distance across different cluster. Okay, then in this case, we can clearly see, is it, so the longest distance, the largest distance is between these 2 points. Is it? Then we also choose the largest one. Is it? Choose the large, but the distance between the furthest element, then we are going to merge them. And then in this case, normally, if we compare these two, is it, this tend to produce chain shape because you choose the minimum, is it? And this one, you pick the largest, is it? You pick the largest, but be careful here, okay? So this is the longest, okay? And we also have maybe the longest this case, and oh, the longest is not this. So between the red and the blue, the longest is this one, is it? And between the yellow and blue, the longest is this one. Is it? Longest is this one. Then among the longest, so we have this 3. So 1, 2, and 3. Is that we have this 3 across different cluster. Then among the 3, you pick the smallest one. The smallest one, definitely we can clearly say it's between the yellow and the blue. Is it? Because it's between the yellow and the blue, that's when you do the merge of the cluster, you merge these 2. Merge these 2 because previous, this is 1, this is 1. And then you merge these 2. Okay, then based on this characteristic, we can see that that's easy to have your merged cluster shape more tend to be spherical clusters. Okay, so that's regarding complete linkage concept. And then, so over here, we also show some of the result. Is it? So here different colors show the different cluster. Is it? So the first pair shows, oh, I got it. So the first one is it show more toward the chained one. The chained one, then it's the minimum. Is it the minimum? The minimum among the closest ones. Is it? So it's more toward the chain type, chain shape. So this one is single linkage based on its distribution. Is it? And then we can see the different color is different cluster. Okay, and this is another type of distribution. Is it? It's more toward the chain type. Is it? Okay, for complete linkage, is it? It's the minimum, but it's further away. So furthest away ones. Is it? So that's why it's more tended to be the sphere type shape. So that's why if you take a look, so this is cluster, this is cluster, this is cluster. So it's more sphere type, is it? And even for this, we can also say it's more kind of sphere type. Okay, so that's the visualization view. We can see the difference between these 2. And regarding the distance, the measuring distance, okay, we can pick some other approaches. So besides a single linkage and complete linkage, we already saw. There is another one called average linkage. So average linkage, then you calculate it from this diagram. You can see you find the distance between every pair. So distance between every pair. This every pair is across 2 clusters. Is it? And then we find summation of them, and then you find the average. Okay, so we find average, and based on this average, then you find the minimum one, and then you group them together. So that's regarding the average link concept. The other one is called centroid concept linkage. Centroid linkage is, so for 2 different clusters. So this is a centroid, and this is a centroid from the second cluster. And you may have another one, as a third one, fourth one. And then you find the minimum distance one between 2 different centroids, and then you merge them together. Okay, so that's regarding using centroid. And the other one is called words method. Okay, so words method, then you compare. So assuming you merge two clusters, is it? And then after you merge, you will have a centroid of this new merged one. And then you find the distance, is it? Then you compare with the original one, the centroid distance to everybody, is it? And you add them together. And in this case, you find the best choice one. Okay, so this is called the words method. So just a different way to find the distance. Okay. And then regarding the agglomerative hierarchical clustering, and there is an algorithm called the Lance-Williams algorithm. And for this algorithm, it's very intuitive because it just gave a single expression. Okay, this is a single expression, but it will apply, did you see, all of the case that previously we discussed. It can apply to single linkage, complete linkage, average, centroid, word. So all of the cases. So in this Lance-Williams, okay, so what this one shows is initially this I and J, this is a cluster, and this is another cluster, samples. Okay, and then we merge both together, is it for most of it? So this is a new sample, is it a new sample? So we already merged these two together, so we call it IJ cluster, is it? Okay, then how are we going to add new samples, is it, when we do the merge? Okay, then so that's called the new samples. We need to find the distance, is it, with the new merged one, how we calculate it. So then we are going to calculate based on this sample with the previous cluster, the sample with the previous one, and this new distance, is it, the distance between these two clusters, IJ. So that's the one between these two. And also this one to the previous I to the previous J, the difference between that. And for each of the case, so here alpha I, alpha J, beta, and gamma, these are some coefficient. Okay, for the coefficient, then in different scenario, you use different coefficient. When you use different coefficient, then they will be reduced to either single linkage or complete linkage. So this is a very smart way, just using a single expression, okay, algorithm, basically, then it applies to all of the cases. So that's regarding the Lance-Williams algorithm, okay. And then next, let's see how the agglomerative hierarchical clustering work. And for this one to work, when we merge cluster, it's called bottom-up fashion. Okay, bottom-up fashion. So here we have a very simple sample. Okay, so this is our data set. So in this data set, we just have 5 students and their scores. Okay, some quiz score, assuming. Okay, so here it lists all of the score. And because whenever we want to do the merge, no matter it's a single linkage or complete linkage, or some other like average, etc., or word. So no matter what, we need to find the distance calculation, etc. So generally speaking, from the original data set, then you can build, we call it a proximity matrix. So the proximity matrix is measuring the distance between the samples. So you are going to measure the distance from one sample to all of the other samples. Is it? So this is student 1. Is it? So the distance between student 1 to student 2, then we can see it's 3. Between student 1 and student 3, it's 18. Is it 28 minus 10? Between student 1 and student 4, then it's this value and this with the offset. Is it? So we just use the simplest case of Euclidean distance. Is it? So it's 10. That's how we come up with all of these values. So in this way, then we can build this proximity matrix. Is it? Okay, with this proximity matrix, then it's easy to identify. Is it? The least distance. We can clearly find the least distance is this 3. So 3 is what? Okay, it's node 1 and node 2. Is it? And then that's why when we draw the dendrogram, we can group these two together. So this is sample and this is a distance. So the distance between them is 3. Is it? And you can group them together. Okay, so after we group them together, then we needed to update the proximity matrix. Is it? And we also update because student 1 and 2 already merged together. When they merge together, then their scores, what we use is we pick the maxima. So we pick a maximum between 10 and 7 is 10, is it? So we put this as our clusters marks. Okay, then we are going to build this new proximate matrix. So this new proximate matrix, then it's between this new cluster and each of the samples, the distance, is it? Then clearly we can find it is this one and this one, is it? So we have 7. So 7 is between what? It's between 3 and 5. So that's the next closest, is it? So then 3 and 5, so that's why we group 3 and 5 together in our dendrogram, is it? Okay, previously we have 1 and 2 together, is it? Now we have 3 and 4. And then based on this, you can continue doing, generate the updated approximate matrix. Then we will find, okay, the next cluster will be 1, 2, and 4 together. Is it? Will be this one. We can. So we build bottom up. Okay. And then lastly, you just get the last 2 together. Is it? So the agglomerate is you start from single sample. Is it? You merge. So we keep merging, is it? Until there is only one cluster. Okay, one cluster. But your goal is to find a cluster, not just group everyone together, is it? So then you can use some cutoff value. Assuming you said, okay, I'm going to use the distance value between the clusters is 12 as a cutoff. So after you cut off, then you can clearly see. So after this cutoff, we can clearly see this is one cluster, this is another cluster. So we can have 2 clusters, is it? And one cluster, they have 3, 5. And the other one, they have 1, 2, and 4 together. Is it? So this idea is called clustering. And this is a hierarchical, is it because we build the bottom up. Okay, and then you choose some cutoff value, okay, for the distance. Then you can select the number of clusters. Okay, so that's the general idea about agglomerate clustering, okay. And once we understand this, and what next, let's see our example, okay. We already discussed the k-means. So now let's see the example regarding how we use the agglomerate clustering to build a hierarchical tree. Okay, so here we didn't use any data set. We just random generate some number, and we have 5 samples, and each sample has 3 features. Okay, so that's the data set. Okay, we generated. And then, so that's not a big deal. That's just as usual. And then over here, it's just to generate some distribution. Okay, so it's, and what over here, it also, so basically this is kind of like our approximate matrix. Okay, so this is just like the example we show. And then you can also specify the distance, okay, Euclidean distance in this case. Okay, so we have the distribution, is it? And how do we pick the linkage? Is it the different linkage? So the different linkage, then you need to import from SciPy. This is not from sklearn, okay, from SciPy. And you import cluster and hierarchy and the linkage as well of the module, okay. And then we can create a linkage object. So you pass in the data set. Is it? You need to specify it's a single linkage or complete linkage or average or what, is it? So we have different ways, is it? And you can also specify the matrix. Okay, so this is just generate the linkage. Okay, and then we can, based on this linkage, so there are, so here just show us, okay, different way. Okay, you can specify the Euclidean and the complete. Okay, so different approaches. Okay, and what we here care more is about the dendrogram. Also be careful, okay, dendrogram is not from sklearn, okay, so here it's also from SciPy, cluster hierarchy package. And to use dendrogram, you need to pass in. So this raw cluster is basically a linkage object. Okay, so you need to pass in that linkage object, okay, for the dendrogram. And then we can draw this dendrogram. So over here it shows the dendrogram, is it? And with a different color, okay. And then what the next one try to show us is, this is also quite interesting, okay, regarding visualization. So we can also attach a dendrogram to heat graph, to a heat map, okay. So in this case, we generate our dendrogram. And because we want to have the dendrogram combined with the heat map, so the orientation of our dendrogram, we are going to put it. So here is a heat map. And then you are going to put your dendrogram on the left. That's how the orientation left means. Okay, and here we also want to sort the data. okay, because we are going to do heat map here, okay, with respect to the clustering, is it? So we have this dendrogram generated, is it? And the dendrogram has the leaf level, so the bottom level, is it? So we are going to order it, reverse it, is it? Order it. And then your datagram, so not data, your data frame, is it? So the data frame, then we are going to reorder it, is it? Reorder. So I location, is it? And it's based on what? It's based on the data, because the leaves give you what? Those ID, is it? Sample IDs, is it? And we are going to base on that information, reorder it. Okay, reorder it. So this is regarding the data frame, okay, not as the original order. And then we can draw the heat map, is it? And the heat map data is from our linkage, is it? So this data is a linkage generated information, okay? And then over here, we can see this heat map, is it? So this is a heat map, and it's reorganized by the dendrogram, okay? So the dendrogram is also showing on the left, okay? So this is regarding the dendrogram. And then next, let's see. For the agglomerate clustering, okay? And this time for the agglomerative clustering, then it's from sklearn, okay? So sklearn does give us direct agglomerative clustering approach. And then you can specify the linkage, is it? And with this, then you will get the cluster. Okay, so once you have the cluster, then you can do the prediction, is it? You can have a new sample and then predict which cluster it should go, is it? And here we specify the number of cluster is 3, is it? Then you will have 0, 1, 2, is 3 different cluster label, okay? And then we can also see, so for this agglomerative clustering, is it? Here we re-specify as 2 cluster, is it? Then the label, we just have 0, 1, okay? So that's regarding this example. And the next, so on our course website, I also posted another example. So this is regarding some grocery stores shopping data, is it? So the shopping data, what we have is the information is, okay, region, channel, fresh produce, milk, or grocery, or frozen. So the classification, etc. Those kind of data is represent number of units purchased by each client for each product, okay? So we have that kind of information. So this kind of information, definitely there is no classification, is it? So what we want here is we want to find some pattern, is it? So we want to group, do some grouping, is it? So then let's see, so total samples we have is 440, is it? So what over here? And based on the original data, we can also see they are not in a similar scale. So that's why we first do data pre-processing, do the normalization, okay? And after we normalize the data, then looks like this, okay? So that's regarding data pre-processing. We normalize our data. And then what next is we want to see our hierarchical clustering tree, etc. So we are going to use the dendrogram. And in order to draw dendrogram, plotting dendrogram, you need to provide the linkage, okay? And here the linkage, we select the word one, okay? And then you pass in the data. So here is the data set, etc. from the grocery store, okay? And then let's see this dendrogram. And we can see, because we have 440 samples. And you can see at the very bottom, there is no way to clarify. It's all crumpled together, etc. But anyway, it also gave us some idea that we can do some kind of cluster, etc. Okay, then what the next one try to show is, it also try to show some cutoff line, okay? Cutoff line on the dendrogram. Okay, so let's see what it shows here. Add a line. Okay, so if you choose the distance as 6 and draw this cutoff line, then from this dendrogram, we can clearly see there are 2 clusters. Is it a green one and red one? Okay. Okay, then next it's just try to show it's too messy, this dendrogram. Is it? How do we have the better view for our dendrogram? We can do some truncation. Okay, so that dendrogram module allow us to do some truncation. So for the truncation, you just specify the truncate model. Okay, the mode. The mode here says it's called last P. Okay, what this means is just to say, show only the last P merged clusters. And then you specify the number for the clusters. Here we said, okay, we want to just last 24 clusters. Okay, last, so the top, because it's bottom up, okay, so the top 24 clusters, basically. And here we also, for this dendrogram, we also want to do some rotation. Is it a font size? You can also specify. Okay, so there are more parameters, that values that you can provide. Okay. And then let's see, this time use the agglomerate is using word distance. So we can see, is it? So over here, then it's very clear. Is it not like the other one? We can, there is no way to identify, is it? And here it also shows us the sample index, okay? And or set cluster size, is it? So it's the cluster size means how many samples already included, is it? So it's much more clear here, is it? And if you still do that cutoff line, it clearly can see that the different clusters. Okay, then what next one shows is we use sklearn's agglomerative clustering model, okay. And here, based on that, we say, okay, how about let's just choose 2 clusters. And you can specify the linkage. We use word. And then for the original data, is it, let's see, each sample belongs to which cluster, is it? So you can clearly get 1 or 0, okay. And then what next one try to show us is we can also find the features that can contribute to the clustering the most. Okay, so we can also collect some information. So here it says we are going to use k-means. Okay, so k-means we can retrieve its feature weights. Okay, and based on the feature weights, then we can find the features that have more weights, contribute to the more to the cluster. Okay, so let's see. Still regarding this grocery store data, etc. This time we say we are going to apply k-means, and we use the 2 cluster. Okay, and then we do the fit predict with this k-mean. And if you wanted to collect its features, then you just collect this data. Okay, within this is the dictionary, Python dictionary, etc. And within the dictionary, then you say, okay, I want to have the cluster center, and this will serve as the features. Is it? Then you will have all of the values provided to us. Is it? And we select the first one. Within the first one, we can see this one and this one. Those 2 values are the largest value. Is it? And all this column so match represent the features. The feature. Okay, so now we know, okay, this is index 3 feature. This is index 4 feature, etc. And based on this, we know from the original column, we know it's milk and grocery. Okay, and because if it's milk and grocery, etc., and then we want to do some scattered plotting. And because with scatter plotting, when we do the plotting, right now, with 2D plotting, we can only pick 2 features, etc. So that's why we pick these 2. Okay, milk and grocery. And then with k-means, etc. So what this one shows, let's see, is this one? Oh, this one, we pick the data. So that data from the normalized data set. Is it? But just those 2 specific columns. Okay, and the label, the coloring here, based on cluster labels. Okay, based on cluster label. Then, so this is use what we first did, the hierarchical clustering. Okay, agglomerative clustering. Then we can clearly see 2 different clusters, is it? And for this scattered plotting, the second one, then it use k-means label. Okay, with this k-means label, then let's see, this is k-means. So we can see it's not compared with hierarchical, this is not as good as the other one. Okay, okay, so that's the idea about hierarchical clustering. And then let's see the last concept in this chapter. The third approach is this dense-based. Okay, the complete name is called dense-based spatial clustering of applications with noise, DBSCAN. Okay, so the concept is we are going to assign cluster label based on what? Based on dense region of points. And so here is a diagram to explain the concept. So in this approach, we needed to have some points. The points going to be labeled. They labeled as core or border or noise. Okay, how we choose. So you have two matrix. You have the minimum points. Okay, you also need to define the radius. Okay, so if a point, so like this point, so minimum point you define, suppose in this case is 3. So within this radius, this point has other 3 points, is it, around it. So then this point is defined as a core point. So it meets the minimum definition of minimum points within certain radius. Okay, another second type of point, like the border point, is what? It is still within the circuits, is it? But within the circuit, the radius, it doesn't have 3, it has less than 3 points around it, is it? So then this point is called border point. Okay, it is still within the distance from the core point. Okay, so then it's called border point. The other one, noise, so it's out of the radius, is it? Then those points called noise points. So that's the definition for this one. Okay, for this one. And then that's why we call, because you can clearly see as this is regarding that core points, is it? And then you have border points, is it? So that's why we say it's density based, but you still consider noise, is it? So what is difference from the previously two that we discussed is it doesn't make assumption about the sphere features like k-means. Okay, it also doesn't do the partition of the data using some cutoff point, is it? So density based, it purely just assign class label on the dense region of the points. So if it's within this dense region, it is. If it is, then we say, okay, it belongs to this cluster. If it is not, then it's some other cluster, is it? So that's the general idea about dense based. Okay. Okay, so that's the idea about dense based. So dense based, because we also consider radius and you need to measure the distance, is it? So distance, we still use Euclidean distance, okay. But it says the disadvantage of dense based is if you have a lot of features, is it? Then it can cause the problem, we call it curse of dimensionality, is it? So previously we learned that term, curse of dimensionality, okay. And with dense space, there are 2 hyperparameters that we need to optimize. So that number of points that you would like to have, that minimum number of points for the density definition, and the radius. Okay, so those are the 2 hyperparameters that we need to optimize. Okay, so that's the general idea regarding the dense based. Okay, then let's come back to take a look at this example. So for the dense based, when we can use it from sklearn, okay, directly to just dense based. Then you need to specify those 2 hyperparameters, okay. The number of minimum number of samples and the radius, is it? And also the matrix for the distance over here we say, okay, we use Euclidean, is it? And then you can train your data. Okay, so that's the idea. Then in this case, we can see for each of the samples that they trained. And then here is the plotting, okay, based on the milk and the grocery. And so here the label, the color label, we use dense based, is it? And with this dense based, then we can see the result is not good. Is it compared with the other two? This is really not a good approach, is it? Okay, so we finish the study of clustering. Okay, so general idea. So next week we will start neural network.